All right, hi AP students. Welcome to your Unit 5 lecture on reaction mechanisms and specifically a look into multi-step reaction mechanisms. So we previously talked about enthalpy and the concept of diagramming energy change through a potential energy diagram in order to track the relative changes between the bond patterns as well as also analyze the activation energy, transition state, and so forth. And now what I'm going to introduce to you is a kind of new concept, which is that reactions usually occur many and most. Many/most reactions occur in multiple steps or in multiple steps or like a series of steps. Okay. Sequentially. Okay. And so what we do is we write and draw reaction mechanisms in order to illustrate these multiple steps. So let me make sure that the way I phrase this makes sense when you guys read back the notes. Reaction mechanism. Most reactions occur in multiple steps sequentially. So what we do is we visualize and model the individual steps via a reaction mechanism. Hopefully that makes a little bit more sense reading it back. So what are some components of a reaction mechanism? Well, of course, you have your relative reactants. The reason I say relative is that when you talk about a series of steps, what happens is that the product of one step can be the reactant in another step. Okay. And then two, you of course have your relative products. Three, let's see, you maybe you have a catalyst, right? If you're lucky, maybe you have a catalyst. You also have what we call intermediates. Intermediates between reaction steps. So these are kind of the four main elements that you'll see in a reaction mechanism series. So why do we see lots of reactions be multi-step? Well, don't forget your collision theory, right? You need to have not only enough collisions, right? You need to have not only have enough collisions, but you need to have collisions that have enough energy, the activation energy, and the right orientation, right? So due to the particular requirements for a reaction to occur, okay, and I'm going to put the note collision theory. Oof. Collision theory. Okay. Often reactions are more effectively completed, by breaking up the process into a series of steps. So, what is each individual step in a series called? We call it the elementary reaction. So, an elementary reaction is an individual step or reaction, okay, within a reaction series. Okay, it's phase one or phase two, or however you want to think about it. So what we say is that when we write elementary reactions, there's a lot of rules that still apply to it, right? Your individual elementary steps are still balanced. okay, are balanced, which kind of makes sense because like even though you're breaking things up into like steps, right? It doesn't mean suddenly the laws of conservation just go out the window. Like you still just start with what you have, right? You're just maybe chunking it out a little bit more in terms of its transformative process, but you still can't just like pull atoms out of thin air and suddenly get them involved in the reaction, right? Also, you should know is that when we write elementary steps, there's often what we call reaction intermediates produced. And a reaction intermediate is a type of chemical species that is produced and then consumed in the sequential elementary step. Okay, it's a transitionary compound. Now, it's not the same necessarily as the complex oh my God, what do we call that? The complex molecule. What did we say above? Geez, McGee. The complex. Oh my God, I'm totally forgetting the name. The activated complex. Oh, goodness gracious. So it's not necessarily an intermediate isn't necessarily this equivalent to the activated complex, but the activated complex can be considered a reaction intermediate. It's kind of like this weird thing, right? An activated complex, we kind of generalize in a one-step mechanism reaction, like it's the breaking and bonding, right? So you might say you have an activated complex for an individual elementary reaction, but what we say is reaction intermediates are actual new bonds that are formed that are then sequentially broken again in the next step, okay? And so what happens is you don't ever find a reaction intermediate in the overall balanced equation. So this would never makes it to net reaction, to the overall final reaction. Okay, so what else do we know about writing elementary reactions and in general their role? Well, what we do is we usually only describe a reaction or collision between one or two particles. And if you're like one particle, that's kind of seems not making sense. Don't worry, it'll make sense later. One or two particles, okay, at a time. So if the whole idea is to break down a complicated reaction, for example, one that involves like three reactants, like statistically aligning three different particles to have the correct positioning and energy to create a reaction is like statistically not existent. So what elementary reactions do is they combat that by saying, well, if we broke down the necessary steps of breaking and reforming, let's start with a one or two molecule interaction first, and then let's tack on more. Hence the concept of breaking things down into steps, chunking it out. So it makes sense then that we would say we usually describe a collision with less particles in order to explain a more likely, probable, efficient mechanism, right? So what you should, we have like, by the way, specific names for that. I'll introduce that to you in a little bit. Okay. We say that a three particle collision is super rare. Super rare. Okay. So that three looks like an S. I realized my mistake. There you go. A three particle collision is super rare. Another thing that you want to keep in mind when writing elementary reactions, okay, is that the sum of the elementary steps, okay, the sum of the elementary steps equals the overall balanced reaction, okay? And then finally, the last thing you want to know is that the rate law of elementary reaction steps, reaction steps, can be can be determined through stoichiometry or stoichiometric relationships. Stoichiometric relationships. So remember how I told you when I first introduced rate law expression that you can never bank on the coefficient or the molar ratio being equal to the reactant coordinate, or sorry, not reactant coordinate, but the reactant order. For elementary steps, you can. It makes it so simple. So what we say is that only in the case of elementary reactions, okay, your molar ratio is equivalent to your reactant order for that particular reactant. This is unique to only the rate law expressions of elementary reaction steps. So here's some key terminology that you're going to want to know, and then we're done. This is such a short lecture today. Whoop, whoop. And tomorrow is also going to be a slightly longer, but pretty short lecture. So yay. Okay. So some key terms. One, we say that molecularity is the number of reactant species that must collide to produce the individual desired reaction, right? So it's specific to an elementary step. So some terms that we use is you can be a unimolecular elementary step where you only have one molecule. You could be a bimolecular elementary step where you have the collision of two species. And then, of course, you could be a termolecular, which is the 3-particle collision, which is super rare. In fact, we very rarely ever talk about termolecular. Okay. Unimolecular and bimolecular is the most common when looking at reaction steps. What we do is we use this molecularity, by the way, is used to assign reaction orders for the individual reaction steps. Okay. Is used to assign reaction orders when estimating. Ooh, that does not look like that word. When estimating the rate for elements, okay, the rate for elementary reactions. Based on the rate determining step. I'm going to abbreviate it RDS. If you're like, what the heck does that mean? Coming soon in the next lecture. Okay. So let me kind of rephrase that because I was kind of like reading and writing. So we use this assignment of molecularity to determine the reaction orders for an elementary reaction, especially when we're estimating what that elementary reactions rate would be, based on what we call the RDS or the rate determining step, the slowest elementary reaction, the slowest reaction step in a series. Okay. So, did not mean to do that. So remember RDS, rate determining step, is coming soon, as in next lecture. So, another thing I want to make sure we're clear on is that the reaction intermediate, right? What's the purpose of a reaction intermediate other than maybe understanding transitional bond breaking and bond forming? Well, something that you need to understand is that the reaction intermediate, okay, is a species, as we know, produced and then consumed and consumed between sequential, okay, reaction steps that allows us to understand the breakdown of a mechanism. You can almost think as reaction intermediates like a molecular checkpoint. Like, okay, I broke this bond. Now I'm here. Checkpoint one. Next reaction series. Okay, I'm going to break this bond that I just made with the reaction intermediate, and I'm going to break it and form a new bond. Checkpoint two, right? So you can kind of think it as like a visual molecular checkpoint in a process. Okay. So, are these real? Is the next question that we might want to ask ourselves when thinking about reaction intermediates. And the answer is yes, most likely. Some of it's a little theoretical, right? Because the transitions are so fast. If you're thinking about breaking down a reaction that occurs at the microscopic level, like you're having to really pause down to like the picosecond, slow down, right? Like slow mo 1000. Okay. But what we do is that we, as chemists, experimentally determine, okay, the possible reaction intermediates. Okay. And that just helps us. They're essentially a theoretical concept that is so confirmed through testing that we can kind of treat them as if they're basically real. Like it is most likely that this reaction intermediate will be formed. And by doing that, it allows us to identify the most likely, and dare I say, accurate reaction mechanism. So they're no just small deal. Like reaction intermediates are as real as they can be because they have to be. Okay, that's it for today. So tomorrow we'll talk about what is this rate determining step and how does that affect our ability to estimate and describe a reaction process and specifically the rate of reaction for both the individual elementary steps and the overall multi-step reaction. So best of luck, you guys. For those of you watching in 2022, it's a starting up Halloween season, so that's kind of exciting. And for those of you watching in the spring, I literally have no idea what season it's starting. Maybe spring, I don't know. But you guys are doing great. We're pumping through all of this, and I hope you guys have a wonderful rest of your evening with such a short lecture. All right, bye everybody.